Welcome back. Now we are going to discuss why the set Q is not sufficient for many purposes where R will be sufficient for those purposes. In other way, we are going to start the analysis of real number system to see that why real numbers can be assumed to be somewhat superior to the set of all rational numbers. Before going into distinguishing R from Q, of course, we have already seen that there exist a few numbers that are in R but that are not in Q. For example, root 2, root 3, etc. But having some special elements, having the position of some extra elements in R compared to Q, is it going to actually make R superior? We cannot strictly say that because having something, some elements extra will not make a set that much special. So we want to see that what are the other properties that may probably make the system of real numbers superior to the system of rational numbers. Before going into differentiating these two sets, we have a few similarities between the set of all rationals and set of all real numbers. Some of the similarities we are going to state here, they are all algebraic in the sense that they're all related to algebraic operations of elements in these two sets. Q and R both satisfy these following properties. There exists an element in these two sets called 0 such that 0 plus a equal to 0 plus a plus 0 equal to a itself for any a in U or R. This is one important property that this property is known as in algebra existence of additive identity. But even before that, remember that addition of two real numbers is a real number. Similar is the case in the case of rational numbers. Addition of any two rational numbers is a rational number. Therefore, they have this plus an operation which we call as a binary operation in Q. It's a binary operation in R also, and dot, which is the multiplication. That's a binary operation in Q as well as R. That is, product of any two rationals is again a rational. Product of any two real numbers is again a real number. And addition satisfies the extra property that there is an element 0 satisfying this condition. Secondly, if we have A in Q or R, we have a B in Q or R, whatever it is, such that A plus B equal to 0 equal to B plus A. This property is satisfied by both Q and R. Third property is that if we have three elements A, B, C in say Q or A, B, C in R, then A plus B plus C is the same as A plus B plus C in both these systems, real number system or rational number system. This is known as associative property of addition. And we have one more thing that A plus B equal to B plus A for any two rationals or any two reals. These properties makes Q an additive abelian group with respect to, of course, additive abelian group inside with respect to the operation plus. Similarly, R is also an additive abelian group with respect to the same plus. In addition, Q and R satisfies all these axioms with addition replaced by multiplication. Therefore, we have multiplicative axioms like in the place of 0, we have to replace with there exists an element 1 such that 0 plus a. Instead of that, we have 1 into a equal to a into 1 equal to a for any a in Q and R, Q or R. And second condition is that if a belongs to R, there exists B belongs to R, or if A belongs to Q, then there exists B belongs to Q such that A into B equal to 1 equal to B into A, but provided that A is not equal to 0. So the extra thing we have to add here is that we have to take A to be non-zero for finding A P such that A into B is equal to 1. The third condition is similar, A into BC equal to AB into C. Fourth condition is also similar. A into B is the same as B into A. All these conditions are there in Q and R. Now we have something extra also that extra condition connects this addition and multiplication in the following way: a into b plus c equal to ab plus ac. This is known as uh, distribution of multiplication over addition, and this is the left multiplication. And here, since a into b plus c is the same as b plus c into a, because we have already seen as the fourth property that ab is equal to ba, we have left distribution of multiplication over addition as well as right. This is left distribution, and we have right distribution also similarly. And we have this property actually relates the multiplication and addition. Q and R satisfies both these properties, and we say that Q is a field with respect to this defined addition and multiplication, and similarly R is also a field with respect to this, the addition and multiplication. So Q and R have exactly the same algebraic properties as far as addition and multiplication are considered. Now the question is that what can make are different from Q. So algebraically, what we are seeing is that they are behaving in the same way. To start the analysis, we now have a definition. Definition is the following. A set A, subset of the set of all real numbers, is said to be bounded above, if you want to specifically say, in R, if there exists a real number b in R such that if A belongs to A, then A is less than or equal to B. That means that we say that the set A is bounded above provided that we can find an element B which lies above all the elements in A. So for example, suppose that our A, this is a real line. Suppose that A is lying somewhere here, up to here, need not necessarily containing all the elements, then we can choose B somewhere here. So if we can take it like that, if we can find element B like this, we say that A is bounded above. For example, suppose that we are choosing A is equal to set 1, 2, 3. We can clearly see that 3 is an upper bound of A. And here there exists a B such that B belongs to R such that A is less than or equal to B. This B is called an upper bound of A. That what we missed. 3 is definitely and we are coming back to this example, 3 is definitely an upper bound, but is 3 the only upper bound of A? It's not exactly like that. So we can take any number greater than 3, and whatever element in A we choose, there is 1 or 2 or 3, and if we choose any number greater than or equal to 3, they're all going to be upper bounds. Any number greater than or equal to 3 is an upper bound of A. So in other words, once we have one upper bound, any number greater than or equal to that is going to be an upper bound. So if A is a bounded above set, then we can find not just one upper bound, there exists infinitely many upper bounds. That is, if A is bounded above, A has infinitely many upper bounds. We have another example. Suppose that we choose A equal to 0, 1, the open interval 0, 1. So we can observe that 1 is an upper bound. 1 is an bound. Not only that, since 1 is an upper bound, we have 1 plus epsilon is an upper bound for any epsilon greater than 0. Another example, suppose we choose b is equal to same way 1, 2. Now we have a question. Is 3 by 2 an upper bound for b? So we can easily see that 3 by 2 is not actually an upper bound because uh, we cannot say that what we want to say is if 3 by 2 has to be an upper bound, then every element in B must be less than or equal to 3 by 2. But that is not actually the case because suppose that we choose 3 by 2 plus 2 and take the half of it. This is actually a standard technique. We have the line here and we have taken 1, 2, this is 0, this is 1, this is 2, and 3 by 2 lies here. And if you choose one point exactly in the middle of 3 by 2 and 2, and this point is going to be less than 2, and this point belongs to B, therefore 3 by 2 is not an upper bound. So this actually gives a technique for, or technique not actually a technique. It's actually a way of verifying whether a given number is an upper bound or not. So suppose that we have a set given to us. Suppose that we want to see whether a number given b is an upper bound for this set or not. For that, what we have to check is if we are very sure that this is not going to be an upper bound, we have to find an element C from that set in such a way that B is going to be strictly less than C. B is not less than or equal to, less than or equal to is not sufficient for us. If at all we want to show that B is not an upper bound of one particular set, we have to find a concrete element C from that set in such a way that B is less than or equal to C. That is the procedure that we have to follow whenever we want to show that some number is not an upper bound. In a similar way, we can define lower bound also. A subset of R is bounded below if there exists a real number L belongs to R such that if A belongs to A, then L is less than or equal to A. That means that every element in A is going to be lying above this L, or L is less than any element in A. Then we say that A is bounded below, and in this case, L is said to be a lower bound of A. If we have L, if we are saying that L is less than or equal to every element in A, then we say that L is a lower bound. Or in other words, how can we define lower bound? Lower bound of A can be independently defined like this. L belongs to R is a lower bound of A if L less than or equal to A for all A in A. Similarly, we can define upper bound also independently without using, without straight away going into the definition of bounded above. So we have lower bound as well as upper bound. Example, n equal to 1, 2, 3, etc. This natural number set, we can clearly see that this is not bounded above because whatever real number we choose, we cannot take that real number to be greater than every natural number because if after every natural number, after every real number, we can find a natural number. How do we do that? Just take the greatest integer function, greatest integer flow of that particular real number. For example, suppose b is a real number, and then if b is negative, or 0. If b less than or equal to 0, then 1 is greater than b, and therefore b not an upper bound for n. On the other hand, if b is in fact in the previous argument we can take it to be, if b is less than, take b to be less than 1, then 1 is greater than b, therefore b is not an upper bound. And on the other hand, if b is greater than or equal to 1, let a is equal to floor of b, that is the greatest integer not exceeding b, and therefore this is going to be again in n, and this is going to be greater than or equal to 1. Now take k plus 1 in n. So we know that the floor of b actually lies between, floor of b lies between what? Floor of b has to lie between b minus 1 and b. It cannot exceed b minus 1 and b. If it's c, if this is equal to an integer itself, b itself is an integer, floor is going to be exactly this, and in otherwise it's going to be uh, b minus 1. So what we are taking here is we have taken k to be b, and if you take k plus 1, then k plus 1 is going to be greater than b, and k plus 1 belongs to n, therefore b is not an upper bound for n. Therefore, n is not bounded above because we cannot find any upper bound for n in the system of real numbers. On the other hand, if we are looking for a lower bound, we can easily see that n has 1 as a lower bound, and any real number less than that is a lower bound. Therefore, n is bounded below, not bounded above. So the set of all natural numbers is bounded below but not bounded above. But if we consider the set of all integers, this is not bounded above, not bounded below. If a set A, if A subset of R is bounded above as well as bounded below, we say that A is a bounded set. A is a bounded set. When do we say that? We say that A is a bounded set when A is bounded above and bounded below. Then A is said to be a bounded set. If A is not bounded, if A is not bounded, but when can this happen? A is not bounded means that A is either not bounded above or not bounded below. See, to say that A is a bounded set, we have to say that A is both bounded above and bounded below. A is not bounded if one of the bounds does not exist. Then in this case, we say that A is an unbounded, A is said to be an unbounded set in R. So these are some definitions about bounds of a set. So what are the things we defined? We defined that A is a set, A is a subset of R, is said to be bounded above if there exists a B such that B is a real number, B such that B is greater than or equal to any element in A. In that case, we say that B is an upper bound of A. The next thing we observed is that whenever we have an upper bound of A, any number greater than or equal to that upper bound, that is any number b plus epsilon, where epsilon is greater than or equal to 0, is going to be an upper bound of A. A set is bounded below provided that there exists at least one real number such that that real number lies below every element in A. That means L is said to be, L can make A bounded below if L is less than or equal to A for any K in capital A. In that case, we say that A is a bounded below set. If A is bounded below and bounded above, we say that A is a bounded set. If A is either not bounded above or not bounded below, we say that A is an unbounded set. Examples for unbounded sets are plenty. We can take the set of for natural numbers, it's unbounded. Set of for integers, it's unbounded. Set of for rationals, it's unbounded. Irrationals, we haven't, of course, proved that it's unbounded because we do not have much idea about how many irrationals are actually there, but that's also going to become unbounded. For a bounded set example, we have for any finite set is going to be bounded. That is actually an exercise for you to show. This is an exercise. Show that the finite set in R is bounded. Any finite set is bounded, and we have open interval 0, 1. This is bounded, and one upper bound is 1, lower bound is 0. Closed interval 0, 1 is bounded. Therefore, any finite interval in the sense that any interval AB, AB, or even mixed intervals in the form A, B, A, B, or A, B in R. These are all bounded. These are all bounded sets. And since finite stays it is, what about the empty set? Is it bounded? The question is the following: is the empty set bounded? So what do we need to see? Can we find an upper bound for the empty set? Can we find a lower bound for the empty set? I'm leaving this as a thinking exercise for you because there is not much to write, but only there is something to actually think. Now, one more exercise in this connection. Show that 1 by 2 is not an upper bound or lower bound for A equal to, now we will take a finite set 1, 2, 3, and B equal to, we'll take an interval 0, 1. So we have to show that 1 by 2 is not an upper bound for this A, 1 by 2 is not a lower bound for this set A, 1 by 2 is not an upper bound for B, 1 by 2 is not a lower bound for this B. I think we have covered the basic definitions of a bounded set. We define a set when will you say it to be bounded above, when will you say it to be bounded below, and what is an upper bound, what is a lower bound, and how many upper bounds and lower bounds can exist when a set is bounded below or bounded above, and whether some special sets are bounded above or not special sets like finite sets, intervals of any kind, empty set, etc. And we will continue with the definition and properties of boundedness, like the greatest lower bound and the least upper bound, etc., in the next session. Thank you.